Now I'm going to explain about example 46. It's a simple question but needs to be understood how it is going to be, because some of the questions are very simple and just analytical and algebra and nothing else in that. Here you need to understand what is the question. Number of 1 functions from set A to itself. Okay, so for easily understanding this, instead of that big paragraph lines as it given in the textbook, so I'll take the arrow diagram that makes it easy to understand. So it is given from the set A to itself. That means domain is also A, codomain is also A. What are the elements that are present here? This is 1, 2, 3, and this is 1, 2, 3. Okay. So here I am going to use the fundamental principle of counting that you have already learned in last year about in the chapters permutations and combinations. If you are going to do some tasks simultaneously in m number of ways, n number of ways and p number of ways. Maybe you are having 3 tasks. The first one is m number of ways, second one is n, and third one is p number of ways. Then the number of ways in doing them simultaneously is their product. That is the fundamental principle of counting. So you have 3 elements here and you need to be matched to these 3, right? So the first element, maybe any of those elements, I am considering the first element 1. It can be matched in 3 ways, 1, 2, 3. So 3 ways can be done, right? So for example, I have matched 1 to 1 only. Okay. Now for the matching for the second one, only 2 are remaining because it needs to be a 1 function. It cannot again go to the first number itself. So it has only 2 more choices. So only 2 ways it can be matched. Okay, let me match it to 3 here. Now I need to check how many ways I can match this. So now you have this number. 2 of them are matched. Only 1 more way, and there is the only way that is going to be useful for matching this. Therefore the number of ways of matching comes to be 3 into 2, that is 6 ways. Therefore the number of 1 functions from A to itself is 6 only, right? Maybe I can change the mapping but still it remains the same. Total 6 number of ways are present. Okay. Now we have the 49th example. The example is, it is asked to show that the binary operations on this set, let me mark the set as A, set A is equal to 1, 2, having 1 as the identity element and 2 as the inverse of 2 is exactly 1. So what is the question in this? This much part is given and you need to prove this and just show that that is true. Okay, exactly 1. So what is the binary operation? Maybe star is a binary operation. So if it is based on the set A, then it has to be a function of A cross A to A. So let me write both of these here. So this is 1, 2 cross 1, 2 to 1, 2. If I do the cross product, I get 1, 1, 1, 2, 2, 1, 2, 2. These are the 4 elements and they're going to the set 1, 2. Since it is a binary operation, all of these elements are going to something else. That means all these elements are tending towards this. And you have 1 as the identity element. If 1 is the identity element, what is 1 star 1? Right? A star E is equal to A. Since E is equal to 1, you are considering this as 1. Therefore, this same element is going to come here. Okay? So similarly, you have 2 star 1 is equal to 2 and 1 star 2 is equal to 2. Okay? Now the last question arises, what is this? Since 2 star 1 and 1 star 2 are equal to 2, 2 star 2 cannot be equal to 2. Right? So it needs to be 1 only in that case. It needs to be 1 in that case. Since it is having an identity element and it is going to be commutative also. Okay. So this is 2 star 2 is equal to 1. That implies this is an identity here. This is identity E. Therefore, 2 is the inverse of this number. This is A, this is B. A star B is equal to E implies B is equal to A inverse. That is 2 is equal to 2 inverse. And this can happen only in one case. That's why this is the inverse of that number. That is the inverse of 2. 2 as the inverse of 2 is only one binary operation. Now we are going to start with the miscellaneous exercise on chapter 1. The first question is like this. It is f of x is equal to 10x plus 7. It is asked you need to find some g for which g dot f is equal to f dot g is equal to I with a set of real numbers. Because it is this one function f is from set of real numbers to the real numbers. So what does this statement say? That g dot f is equal to an identity function, f dot g is also an identity function, right? Both of them are identity functions. So this is very similar to the thing that we have learned in inverses, right? Inverse, if it has to be an inverse, then its composition of those two functions should be always an identity function. That means g is same as inverse of f, right? That's simple, and you can need to ask how it is. Y is equal to 10x plus 7. Okay, now y minus 7 is equal to 10x. X is equal to y minus 7 divided by 10. Therefore, the function g is g of y is equal to y minus 7 by 10. Only this is the function. That's it. You need to find the inverse. So after that, you need to just prove that this is equal. Just substitute that over there and you will get that answer. The second question is all about this. This is the function of n, and it's also considering the natural numbers here. So here it is n minus 1 when n is odd, n plus 1 when it is even. Okay. So the thing here is you have already seen the example 12, which is very similar to that. There it was n plus 1 when it is odd and n minus 1 when it is even. This is just the opposite of that. That's it. So first you need to prove that it is 1 1 and on 2 to show that it is invertible. Okay. After that you are going to get this function like this, because when you subtract 1 from an odd number you get an even number. So when you get an n is even in the inverse, here you have subtracted 1, here you are adding 1. That's the thing. So when you add 1 to a even number, you get a odd number. So from the odd number you are going to subtract this 1 here. That's it. So you are going to get the inverse of f over there. Okay. Now next, let's move to the third question. Third question is composition of the function. Composition of the function. You have f of x is equal to x square minus 3x plus 2. Plus 2. You are asked to find f of x. F of x is f dot f. Okay. Same as f dot f. So what does it mean? Now f of x is x square minus 3x plus 2. Now I need to substitute the whole term in place of this x. So it's going to be a very hard task now. X square minus 3x plus 2 whole square. Let me write this part. Okay. This is x square term. Next is minus 3x. Minus 3 into x square minus 3x plus 2 plus 2. So now you need to expand. This is a plus b plus c whole square, or I can write it as, it becomes, what is the expansion for a plus b plus c whole square? That comes to be a square plus b square plus c square plus 2ab plus 2bc plus 2ac. Okay, this you are going to get here. That is x raised to 4 plus 9x square plus 4 is what you are going to get the square terms. Now we need to get the two terms, 2ab terms. So this is minus 3 and 1 2 here. No, 1 here. So minus 3 into 2 comes minus 6. X into x square is x cube. That is AB now. BC. BC is 2 into 3 is 6. 6 into 1 more 2, 12. And there is a minus sign. So minus 12x. Okay. Now we are going to add AC now. So this is 2 into 1, 2. 2 into 1 more 2, that is 4. And you have a positive sign, that becomes 4. only x square terms there here. Okay, now just expand this. This becomes minus 3x square plus 9x minus 6 plus 2. Okay, this is minus 3x square. All the x square terms I am going to underline now. Okay, I'll round off the cube terms. Only one cube term is there. Okay, I'll do like this for the x terms. Okay, remaining are all the fourth power or the just the digits. There becomes x raised to 4. 9 plus 4 is 13. 13 minus 3 is 10. So it becomes 10x square. 10x square. There is one more term, like x cube term. Here the x cube term becomes minus 6x cube plus 10x square. Now only the number, no, 12x is remaining, right? 12x and 9x you have. So 12x minus 12x plus 9x comes to be minus 3x, and you have plus 4 plus 2, that is 6. 6 minus 6 is 0. So this much is the answer now, right? Now we'll move on to the next question. Now we have the fourth and fifth question of the miscellaneous exercise. So the fourth question is all about this function f of x, that is x by 1 plus mod x. Because it's a mod x, there are two cases that are arising. So I can define this as x by 1 plus x when x is greater than or equal to 0. Then when it is less than 0, you need to have another case. So x becomes minus x in that case. So this becomes 1 x by 1 minus x. So to prove, you have to prove that it is 1 1 and on 2, right? That is the question. So for proving 1 1, you have three cases. For taking, you have to start with f of x1 is equal to f of x2, right? So in first case, x1 and x2 are positive. Here both are negative in the second case. The third case comes with one positive and another one negative. In that case, what do you need to do? Okay, you have in the third case, right? The third case is a little bit how to conclude that x1 by 1 plus x1 is equal to x2 by 1 plus 1 minus x2. Okay, so what do you get here? So just by seeing I can tell that here in when x is positive, x by 1 plus x is also positive. Okay, when x is positive, x by 1 plus x is also positive. When x is negative, x by 1 minus x. So this term is positive now because it is 1 plus modulus value of that or 1 minus the negative of that. So it comes to be this is positive, but the numerator is negative, right? X is negative, therefore this is negative. Since therefore this case cannot arise at all. This case cannot arise. This next part is just to show that it is an onto function of just based on taking it opposite values. Just when you take x is greater than 0 or y is greater than, just like that. Okay, now we have the fifth question. Fifth question is just to show that it is an injective. Injective, it means 1 1 function. If it has to be 1 1, then f of x1 is equal to f of x2. Just write x1 cube is equal to x2 cube. X2 cube. Therefore x1 is equal to x2. Therefore f is 1 1. This is a very small and simple question. Now we'll go on to the sixth question. Okay, we have a sixth question and the seventh question. I think I need not explain that because the answer is already given over there. It is given hint. Consider this is just asked to give the examples, right? So you are just going to do that. Now we are moving on to the eighth question. Now we have with us the eighth question. The eighth question is relating to this. This is a power set. What do you mean by the power set of x? X is all the subsets of x. The set of all the subsets of x forms the power set, right? That you have learned already in 11th standard in the chapter sets. So here R is a relation. A, the question given is A is related to B if and only if A is the subset of B. I have just written in the form so that you can easily understand. And A and B are belonging to this set. So they are the subsets. So they need to belong to that P of X. Okay. So we need to just tell whether this is an equivalence relation. That's what the question is. Are an equivalence relation. For equivalence relation, it should be reflexive, symmetric and transitive. Let us try with everything. So A is related to A if and only if, this is the symbol you use for if and only if A is the subset of A, right? That is true. A is a subset of A. Therefore, it is reflexive. Now we'll go on to symmetric. If it is symmetric now, symmetric means if A is related to B. Okay, A is related to B, that implies that A is a subset of B. Okay, then see, but okay, let me show the Venn diagram how it is represented. So say this is a set B and it contains the set A. This is a set A and this whole thing is set B. So from this you can understand that set A is completely belonging to this B. It is a proper subset of B. But that means that B is not a subset of A. Right? Does not contain only A but also some other elements over there. Maybe so many elements are there. And here 4-5 elements are there. So you can understand that B is not always a subset of A. That implies that B is not related to A. Therefore, not symmetric. The given relation is not symmetric. That implies that R is not an equivalence relation. Not an equivalence relation. Okay. Okay, now we go moving on to the 9th question. Okay, you have the 9th question. 9th question is about binary operations, right? So now we have a star is a binary operation that is operated along this power set of X. X is a set, so it's the power set of that is a set of all the subsets that you have already understood in the previous question also. So what does it do? So if you have two sets like this, you are going to get the intersection of those two sets in P of X. Both of them are belonging to P of X, and you are asked to show that X is the identity element and only X has the inverse. Okay, so for an identity element, let M, let be any other number or any other set, M be the identity element. So how do you explain this? So it should be A star M is equal to A, that is equal to M star A. Since this is the intersection, right? Intersection is the operation which is commutative. So I can leave out this condition and only one condition is applicable. Okay. So this becomes A star M becomes A intersection M. A intersection M is equal to A. Intersection M, right? P. Intersection M. So what does it mean? A is somewhere like this and this is M, right? This is the Venn diagram. So this means that the common portion for both the sets is the whole set A. That means this is a proper subset of M. So but here A, for every A that is belonging to that P of X, this is possible only if, see, you need to have all the other subsets should be the subset of X only because it is belonging to the power set of X. Therefore it is possible only if M is equal to X. M, I am just considering some identity element, sorry, it should be a set, right? Here it should be a set. So generally we just talk about element identity. Let this be the identity. Okay. Now I am going to the next part, that is only x has inverse. If it should be like only x has inverse, then it should be a star b is equal to the identity element, that is x here, that is equal to b star a. That is the same condition you are going to have because it's a commutative one, because this is the intersection, right? So that becomes a in intersection b is equal to x for a and not for every, where a and b that is belonging to which is the power set, right? Okay, you got this much. So a intersection b should be x. The whole set is x, right? Showing the Venn diagram. So if I need to have two different elements, it may always cover the less than the x, because x is the whole set. So both of them need to be x here. Both of them need to be x such that their intersection comes to be x. Right? There is no set that is bigger than x because it is the set of subsets of x. So there is no element that is left out in the intersection. At the end of intersection, you are going to get x, right? So both of them should be x. Therefore, only x has inverse, or it is invertible. Okay, and its x inverse is equal to x. If you want, you can write this. Okay. Now we are going to the next 10th question. Now we have the 10th question. 10th question is asked to find the number of all the onto functions from the given set. It is a finite set, maybe some number up to n. N can be some other number like 12, 15 or something. So you need to find the number of onto functions. Since it is a finite set, I can tell that it has to be a 1-1 function. See, if you have to show by an arrow diagram, say if I mark this as set x, you will have, I'll take only 4 here. 4 out of this, need not take all of them. There are 4 points. So if it has to be an onto function, it has to be 1-1 also. Because all here the number of elements is n, and here also number of elements is n. So if all the elements in the codomain has to be covered, that means that only one can be mapped to the one of the elements, right? Not more than one can be allowed marked to that. So it has to be a 1-1 function. Therefore it has to be a 1-1 also. That is the thing. Now the question turns to be the number of all 1-1 functions from the set itself. Okay. So the number of 1-1 functions, as we have already done in the example. What was the example number? The example number was 46, in which we used the set 1, 2, 3 to find the number of 1-1 functions. We found out that it was 3 factorial over there, right? Similarly you are going to get here, because one of them is mapped to this, you will get n2, next was 1 less than that becomes n minus 1, then n minus 2, and so on. So this comes to be n factorial up to 1, right here, up to 1. So this is n factorial. Therefore n factorial number of onto functions, onto or 1-1 functions, onto functions from the given set is possible. From the given set to itself is possible. This was a simple question, right? Now we'll move on to the 11th question. Now we have the 11th and the 12th question. Here you have the 11th question with 2 sets given, S and T. S contains elements A, B, C, and T contains elements 1, 2, 3. You are asked to find F inverse if it exists. The question says if it exists. Okay. So the first one was given F is to be A3, B2, C1. If F has to be existing, it should be 1-1 and onto. That is, if it has to be invertible, it should be a bijective function. So just by seeing you can understand that it's a bijective function, because 3, 2, 1, all of them are considered here. 3, 2 and 1 are considered, and one of them is mapped to only one of them. That is, A is mapped to 3, B to 2 and C to 1. Therefore it is a 1-1 function. So how need to find the F inverse? It's very simple one. This is A, 3. So I need to just interchange and write 3a. This is b2, right? So it becomes 2b. This is 1c. This is f inverse. Now the second part of the question is f is equal to a2, b1 and c1. Right? See, you can observe here that only 2 and 1 are included out of this elements that are contained in that set T. So therefore it is a minimum function, right? And it is not onto also, it is into function. Therefore f inverse doesn't exist. It doesn't exist. Okay. Now we have the 12th question. 12th question is having two binary operations, that is star and dot. So the star says that you need to find the modulus value of a minus b. This is a dot b is a. Now you are asked to show that whether it's commutative and associative. It's given in the question that star is commutative but not associative, and dot is not commutative but associative. Okay, you just prove that. Now you just show that a star b. What is a star b? Modulus of a minus b. B star a is equal to modulus of b minus a. Both are equal, right? Both are equal. A star b is equal to b star a. Therefore it is commutative. Okay, now we have here a dot b. A dot b is equal to a, but b dot a is equal to b, right? You are considering only the first one here. See, you are going to get only the first element. B, that is the second element, is excluded over here. Here you can find that a dot b is not equal to b dot a, right? Therefore it is not commutative. Now we have the associative property. Associative property is about a star b star c. I'm going to take one of them. So this becomes a star of modulus value of b minus c. Okay. Now it is modulus value of first minus the second. That is a minus modulus value of b minus c. Okay. Now you have this much. Now this is a star b star c. How do you get this? A star b is modulus of a minus b star c. Now when you apply this, it becomes the modulus value of first minus the second. First one is modulus value of a minus b minus c. Just by observing you can understand that here you do not have modulus sign a inside the modulus sign, and you have c inside the modulus sign here. But that is opposite over here. Therefore they are not equal, right? A star. Therefore it is not associative. Not associative. Here you have you need to prove that it is associative, though a dot b dot c. B dot c, because only the second element is excluded, only the first one is there. This becomes a dot b. Okay, you are excluding again the second element. This comes to be a here. Okay. Now the second part is a dot b dot c. Again you are excluding the second element. This becomes a dot c. Second element is again excluded. This comes to be a. Therefore associative. See, both of the sides you got a itself. That means both are equal, right? So you are considering only the first element out of there. Now you also have a subdivision for this. After you have to prove that. Generally if it is a very long question, you get that subdivisions. Maybe a 6-mark question or something like that. So in this question you have you need to prove that it is a star b dot c is equal to a star b dot a star c. Okay, so let me take the right hand side and come to the left hand side, or I'll find out both of them. So let's assume LHS is equal to a star b dot c. So the dot function says you need to exclude the second one and only first one is kept over there. So b dot c becomes b. A star b stands for modulus of a minus b. It is already clear. Now you have the RHS. RHS is a star b dot a star c. So this says modulus of first minus second, modulus of first minus second, first minus second dot modulus of first minus second. So the dot function the operation says you need to take only the first one, that is modulus of a minus b. So you have just proved the same thing, that is LHS is equal to RHS, right? LHS is equal to RHS. Therefore this concludes the given statement. Now I have the 13th question. 13th question is similar to the previous ones. That is the 9th question where you had the binary operation involving the power set of x here. So there is a different operation here. So if you have the operation star with a and b, you get a minus b union b minus a. Let me show the Venn diagram and just simplify this complicated one. Right? So if I have one set A and this is set B. This is A and set B. What does A minus B stand for? A minus B stands for the things that are present in A but not in B. That is all this portion. Okay. Now what is B minus A? B minus A stands for all the things that are present in B but not present in A. That comes to be this area. But you know that the whole area is A union B. Right? That is A union B. And you are going to subtract A intersection B from that. This is the intersection part, right? This part is not going to be present in this sum, right? So the whole thing you get when you use the union. When you use the intersection, you are not going to get this. You are going to subtract that. So this comes to be A union B minus A intersection B. That makes it simpler to understand that. Okay, the question is, now you need to show that the null set, that is phi, is the identity and all elements are invertible with A inverse is equal to A. So if it has to be an invertible, if it has to be an identity, so let me take the identity element should be E. Okay, let it be E itself. Maybe some, it should be a set, but so it should be an identity element. A star E is equal to A, that is equal to E star A. Okay, let me denote the set to be E itself. So now what you get is A union E minus A intersection E is equal to A. Okay. The right hand side what you get is A union E minus A intersection E. So it's the same, I think, right? Yeah, ulta pulta it is. That's it. So you are going to get the same condition in both the cases. So what does it say? So let us have two of them here again. This is E and this is A. So what is A union E? The whole thing minus this thing comes to be A itself. That means that E is the subset of A. Okay, let me change the diagram now. This comes to be A and this is E. Right, you now get to this subset. Okay, from this what do you get? E to B. Here you need to get the set A itself, right? So the intersection should be 0 because it's a subtraction. So maximum amount of union you can get here should be A and this should be 0 or the null set here, right? So let me take some like this, and you have some element like this E and this is A, right? So what is A union E comes to be the whole thing and A intersection E comes to be this thing. So the remaining part should be A itself, right? But if it is a subset of E, that cannot come under that, because when you take the intersection, that comes to be E over there. That time A minus E cannot be equal to A, right? The only case when it can be equal to A is when it is phi. Therefore, phi is the identity. Let me explain once more using this Venn diagram. So you have A and maybe some other set E that you are considering to be the identity. So the function says, now I'll take this and explain. This is A minus B union B minus A. Okay, B minus A means here all the things that are coming here and all the things that are coming here. Okay, you are only excluding this middle part out of that. So what do you need to get here is such that the union of both of them has to be maximum of A, and it has to be A in this case. Okay, So this, you can just move this such that it becomes a subset of E. Yeah, maximum of E. So I feel that it should be a subset of E. So now what I should do is I should take this one, right? It should be a difference here. The maximum it can come here to be E only. I'm sorry, the A itself, because it is the maximum out of this. So the intersection should be minimum out of that. So the minimum intersection is only 5. That is possible. Okay. We'll go to the next part. Next part is just to show the inverse, that is maybe A and B is the inverse of A. Then you have to get 5 over here. Okay. So I'll use this expansion, that becomes a little bit easier, I think. So this is here A minus B union B minus A is equal to 5. Okay, that means that both of them are 5 because it's a union, right? So both of them should be 5. Therefore A minus B is equal to 5. 5 stands for a 0 set. That means the element set which does not have any element. That means that A is equal to B. B, I had already considered it to be the inverse of A, right? Therefore A inverse is equal to A for every A that is belonging to that P of X, right? Therefore you're going to get this as the output here. Okay, next we'll move on to the 14th question. 14th question is about binary operations. Star is a binary operation of the event set, that is 0, 1, 2, 3, 4, 5, and you have so many elements like that. So what is the binary operation says that you need to find the sum of those two if it is less than 6. Otherwise you need to subtract 6 from that sum if the sum is greater than or equal to 6. So it's a binary operation, that's why you need to have same set. So let me name this set to be A. Therefore star has to be only from A cross A to A itself. Therefore when you get like this, you are going to land up on a number of elements in the same set. So for easiness to understand this one, so I'm going to draw the operation table. 1, 2, 3, 4. 1, 2, 3, 4, 5. Only that much, right? Here it is 1, 2, 3, 4, 5. So what does it say? 0 plus 0. Okay, it is 0 itself. I'm just going to write, fill up this table. I feel you know how to fill up that table. So this is 2 plus 0, 2, 3 plus 0, 3, 4, 5. Similarly, you are going to get here 4, 5. So what is here? 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5. Okay, let's leave this. This comes to be again 3, 4, 5. What is the number here? 2 plus 2 is 4, 3 plus 2 is 5. Here also I'm going to get 5. This is 2 plus 3, right? So we have some more elements that are remained here. So what is 5 plus 1? 5 plus 1 comes to be 6. So 6 is greater than or equal to 6, right? So you need to subtract 6 here. That comes to be 0. Similarly, you get 4 plus 2, 6. So it is 0. 3 plus 3, that is 6. So it comes to be 0. 2 plus 4 is 6, again 0. Here also 0. So I can just see the pattern and just go on filling this. 1, 1, 1, 1. This is 2, 2, 2, 3, 3, 4. Okay, this is the way of filling it. After filling so much, you are asked to find the question. In the question, you are not asked to do the operation table and all. This is just for easiness of doing that. Okay, the question is to show that 0 is identity element of this. So if I do any 0 from the operation table, I can just show that 0 star any element is always equal to that element from the operation table. From the operation table, or I can just tell that A star 0 is also equal to A from the operation table. This is the first element, this is the second element, A, B. Okay, if I consider always, it comes to be the same number, 5, 5, 4, 4, 4, 4, like that, right? Where it is considering the 0. Therefore, 0 is the identity element. That is the easier way to conclude that, because you are going to get a number of cases over there. That's why it's easier to make the operation table and just explain what is given over there. Okay. Now we have to just prove that the inverse of a number can be either minus A 6 minus a itself, or it shall be the 0 has its inverse to be 0 itself. So just by seeing this, what does it mean? So 0 is the identity element. So if I do a star b, then it should be equal to 0, right? So from the operation table, again you are going to the operation table, there are a number of places where you have 0, 0, 0, 0, 0, 0. So if I consider this as the first element, and the other element that you get from the horizontal line is the inverse of that. So inverse of 0 is equal to 0, right? Because 0 star 0 is equal to 0. A star b should be equal to 0 to find the inverse, right? So similarly, you have 1 inverse is equal to 5, and so on. So always here you find out that it comes to be 6 minus that number. So inverse of a is equal to 6 minus a. That is what you find out from this operation table. 6, here you find 1 and 5. So 5 is equal to 6 minus 1, right? Here you have 4. 4 is 6 minus 2. Here you have 3. 6 minus 3 is 3. Similarly here also. That is 6 minus 5 is equal to 1. That is just what you have to explain. You can just write it is from the operation table, because you have done the operation table, right? Then you're not going to bother about much about the things that are have to be written again out of that. Okay, now we have the 15th question. 15th question is about set A and set B. Set A has minus 1, 0, 1, 2. B has minus 4, 2, minus 2, 0 and 2. So in the question is asked, there are two functions f and g that are from A to B in both the cases, and you are asked to find whether f and g are both equal functions. Equal functions means the value of both of them. If you apply for a value of x, say x if I put minus 1, both of them should give the same value. That's what the meaning of f and g are equal over there. So for that we'll find, because there are only 4 elements, I can go on finding the answer of the both of them. So now we will have f of minus 1, f of 0, f of 1 and f of 2. Okay, this one is x square minus x. X square is minus 1 whole square minus 1. This becomes minus 1 whole square is 1. 1 minus 1 is 0. So f of 0, everywhere it is 0, you get 0 only, because there are no x terms without x. So now you have f of 1. 1 you are going to apply 1 here, that comes to be 1 square minus 1, that is 1, no sorry 0. If it is 2, f of 2, you are going to apply 2 square minus 2, that is equal to 4 minus 2, that is equal to 2. Therefore 2 is belonging to the 0 is also belonging, so there is no problem here. Okay, now we have g of minus 1, g of 0, g of 1 and g of 2 you are going to find here, and just say that they have to be equal or not. Okay, g of minus 1, that becomes 2 into modulus of minus 1 minus half minus 1. This is 1 and half comes to be 3 by 2. 3 by 2 minus 3 by 2, so its modulus value comes to be 3 by 2. So this comes to be 2 into 3 by 2 minus 1. This is 3 minus 1, that is equal to 2. Right? So I feel that something is wrong in this first part also. So this has to be minus of minus 1, that comes to be 2 here. So this is also 2. Somehow I should make it equal, right? Now we have some 2 here. 2 into 0 minus half comes to be minus half itself. Minus 1. Minus is going to be cancelled because it is of modulus value. So it comes to be 2 into half minus 1. Half and half. 2 is going to be cancelled. 1 minus 1 is equal to 0. 0, 0. Okay, no problem. 1, 2 into modulus of x minus 2, that is 1 minus half minus 1. So this comes to be 1 minus half is half. Half into 2 is 1. 1 minus 1 is 0. So 0, correct. Now we have 2 here. 2 into modulus value of 2 minus half minus 1. So I feel I am going to do the same value, because you have 2 into 3 by 2. Here negative sign is extra. Here there is no negative sign, because 2 minus half is 3 by 2. Right? 3 by 2, it becomes 2 into 3 by 2 minus 1 half. You are going to get cancelled. You get 2 here. So just by seeing you can understand that f of x is equal to g of x. F of x is equal to g of x for every x that is belonging to the set A. For every set that is belonging, it is not there. For every set that is belonging to the set A. Now we are left out with the MCQ questions. Now we have with us the 16th and the 17th question, and both are based on the set A, that is 1, 2, 3. So the 16th question is you have to find the number of functions or the relations which are reflexive, symmetric and not transitive. Okay, so let me write maybe some relation in such a manner. So if it has to be reflexive, so 1, 1, 2, 2 and 3, 3 should be present. Okay, then it should be symmetric now. So it is containing 1, 2. Therefore, if it has to be symmetric, 2, 1 should also be present, right? 2, 1 should also be present. Then you have 1, 3 here. 1, 3. If it has to be symmetric, 3, 1 also should be present. I think this many will be enough, because in this case it is not transitive. I can say how it is not transitive. You have 1, 3, 1 here, right? 3, 1. 3, 1 is present and 1, 2 is present. 1, 2 is belonging to the relation, but 3, 2 is not relating. 3, 2 does not belong to that relation. Therefore, you can just tell that it is not transitive, but it is reflexive as well as symmetric. So this is the first one relation. Now next there are only 2 more elements that can be added over here, that is 3, 2 and 2, 3. If I add both of them, it becomes transitive. So this is the only one relation that can be reflexive, symmetric and not transitive using the 3 elements. So it is going to be the option A. Option A. So the next question is based, you need to find equivalence relation, number of equivalence relations with 1, 2. If it has to be an equivalence relation, it should be reflexive, symmetric and transitive. So the relation could be 1, 1, 2, 2, 3, 3. This makes it reflexive. Okay, so it should have 1, 2, right? So it has to be 1, 2, 2, 1. It should be symmetric, right? That's fine. So this becomes the equivalence relation. This is one equivalence relation. Now there are some more of them to be added. So I can add after adding 1, 1, 2, 2, 3, 3, that makes it reflexive. Then you have 1, 2, 2, 1, that much should be present. Then again you are going to add 1, 3 and 3, 1. So this makes it not transitive as in this case. So I need to add both of them again. That is 2, 3 and 3, 2 also should be added. This makes it full. That is a full set. That is a power set of that. Sorry, not the power set. It's a ordered pairs of all those things. So this becomes one of the equivalence relations. This is another equivalence relation. Therefore, there are 2 of the equivalence relations which contain 1, 2 in them. So this comes to be the option B. Option B. Moving on to the 18th question. 18th question is initially has to define the composition of 2 of them. Okay, the first function f given is a signum function, and the second function is the greatest integer function. It is called as greatest integer function. It is represented to be like this, greatest integer function, and the first one is a signum function that says f is equal to, okay, f of x is equal to 1 when x is greater than 0, 0 when x is equal to 0, minus 1 when x is less than 0. These are 3 cases. Here you are asked to find, does f dot g and g dot f coincide in 0, 1. They have asked one interval 0, 1. It is asked whether f dot g and g dot f coincide. G dot f coincide. So I am considering only from 0 to 1 in the case. So it has to be a positive. it is positive, right? Just let me write, this is positive, and greatest integer of that value is equal to 0 in such a case. Okay, these two things you need to just remember. So what are going to get here? This is f dot g of x. So f of g of x. G of x stands for the greatest integer less than or equal to that thing. So f of, like this is the greatest integer. So from here, if it is belonging to this, it is going to be 0. This becomes f of 0. So when x is equal to 0, I have to apply here, this comes to be 0, right? So in that interval, f dot g becomes, of any number, becomes 0. Now we have to take for this f g dot f of x, that is g of f of x. So here you find that it is not, 0 is not included and all the remaining numbers are positive. So when x is positive, this f of x becomes 1. So this is g of 1, or this is the greatest integer function, right? So I can represent it to be g of, this is 1 itself. So greatest integer less than or equal to 1 comes to be 1 only. So you can find that in the interval 0, 1, here both of them are not going to be equal. F dot g is not equal to g dot f in that given interval. That's why you can just tell that it is they do not coincide in that given interval. Okay, now we are moving on to the 19th question. 19th question is an MCQ question based on the number of binary operations that can be done from a given set. So the given set here is A, B. The set A, B, number of binary operations. So maybe star is a binary operation, that is from A, B cross A, B to A, B. Okay, so this, if I do the Cartesian form, it becomes A, B, B, B. That is going to A, B. If I need to find the number of binary functions of this, so I have to take this to the value of those. So the number of values this operation can take is 2, and the number of values this operation can take is 2. This 2, and this also 2. By fundamental principle of counting, I can just tell that all of them are going to be done in two ways. So when I do them simultaneously, I need to multiply them. That comes to be 2 raised to 4 or 16 ways. 16 ways of doing. It's an MCQ question, right? So the option comes to be option B. Option B. Okay. Thank you.